Good morning. Welcome to the Tao of Hardware, the Tay of Implants in South Seas GH with Joe Fitzpatrick. Before we start, a few brief notes. Be sure to stop by the business hall located in Bayside AB. The Black Hat Arsenal is on in the Palm Foyer on level 3, and of course the Arsenal reception at 1700. If you haven't picked up your merchandise, today is your last chance to visit the Black Hat swag and bookstore. And also be sure to visit the Kali Linux lab in Mandalay Bay. I heard it's pretty cool. Also, thanks for putting your phone on vibrate. Without further ado.
Hey, how's it going? I'm actually going to double check and make sure no one modified the sign, because I've seen a lot of interesting signs going around. Don't know how that could happen. Good morning. This is Tay of Hardware, Tay of Implants. Who here likes hardware? Who here likes all the hardware talks at Black Hat? Who here would rather be at the SC talk? The Secure Enclaves talk? Actually, no, I'd rather be here. But there's a pretty cool Secure Enclaves talk going on right now that I really wanted to see, but oh well. You're stuck with me instead. You probably actually get a seat in here. You might not get a seat in there. So welcome. I'm Joe Fitzpatrick. My background is electrical engineering with some CS and InfoSec mixed in there. I've been over 10 years doing professional hardware stuff. I did silicon debug on CPUs. I did security research, hardware pen testing of desktop and server CPUs, both pre and post silicon. So you think of a code review, you think of like mowing through lines of C or JavaScript or whatever language the kids are using these days. Do the same thing, but with Verilog. It's a lot uglier because Verilog is ugly. The past 5 years, I've been doing hardware security training, the past 4 with my own business. Right now, I am teaching applied physical attacks on x86 systems. Just finished a 4-day class. Ask anybody who may have been in that class how it was, because I think it went really well. I also have a similar class, applied physical attacks on embedded systems, which focuses more on MIPS and ARM targets as well. I'm also one of the organizers of B-Sides PDX. If any of you need an excuse to come to Portland, it's a really awesome place. B-Sides PDX is there. Come bug me. I'll tell you when it is, and it'll be great. It'll be fun. You'll have Voodoo Donuts, and you'll get to see all the places in Portlandia. But you're not here to hear about that. You're here to hear about hardware or something. So there might be some confusion with the title of this talk. It's not this Tao. It's that Tao. It's the philosophy. It doesn't have anything to do with Tailored Access Operations, Department of the NSA. Don't worry about that. Any confusion is entirely coincidental. So what is Tao? Tao is this Chinese philosophy. It's the absolute principle of the underlying universe, combining the principles of yin and yang. It's the way, the code, the behavior. It's just the natural order, right? So the Tao of hardware is that hardware really is the absolute that underlies everything in the world of computing. No matter how much time you spend making your cool software security stuff, it's still got to run on someone's hardware, and you got to hope that that hardware is in good shape for you. On the other hand, Tay is the Chinese philosophy of inner character and inner power and integrity. And so the Tay of Implants in this case is harnessing and understanding the inner strength of these tiny little minor additions that we can make to a system. Cheers. It's just water, I swear. So Lao Tzu is the author of Tao Te Ching, or the purported author. And he said, do the things while they are simple, and do the great things while they are small, right? We talk about all the things we can do in hardware, and we have these systems where people chain like 15 vulnerabilities to go and like pop calc, right? Wouldn't it be cool if we could just get down to the lowest layers and like do it where we only have to flip one bit or twiddle one byte or pull one wire and bypass all that difficult software stuff? I don't know if you've noticed, I don't really like software nearly as much as I like hardware, mostly because it's hard, and I'm not very good at the software side of things. The hardware stuff I love. It's fun. It's wires. I can see it and touch it. Software, whatever. So hardware implants pre-2013. There's some prior art, but not much. When people thought about hardware implants, the term probably didn't have as much of a use back then, but what people thought of that was basically these like mod chips for game consoles, right? This is really the only thing we had where you would go and buy a piece of hardware and stick it in another piece of hardware and do something cool. And you could use these, and you could play backup games, and you could like play homebrew games, and there are no illegal uses of these things at all. The point is, this is a hardware implant, right? We got this tiny little circuit board. We solder it in these nice little well-marked places. It's all lined up. It's very easy to use. This is a very consumer-friendly hardware implant, isn't it, right? But what happened, Der Spiegel had this article where they have the catalog that advertises the NSA Toolbox, the Ant catalog. Who knows if this is legit or not? Don't worry, I'm not going to be showing any possibly confidential or top secret documents on the screen, so you don't have to shield your eyes if you happen to have regulations or rules about that. Anyway, the media saw this, they loved it. I was like, whoa, look, this is magic. They can do magic with hardware, and it's really not magic. And we were like, hey, we could do that, so we did the NSA playset. Who has been to like an NSA playset talk or played with an NSA playset toy at some point in time? It's fun stuff, isn't it? So the point is, like, hey, we can do this. Let's start building this stuff. So we did. We started building these things. What we learned is that malicious hardware implants are real. Someone is doing a lot of work making them, or at least making pretty convincing PDF files advertising them. Hardware implants don't live in a vacuum. This is the big key one for me. Like, I think I got hardware access. I can do everything I want to. I don't stop to think that, like, if I can extend that to software access, then someone who knows what they're doing can do a whole lot more than me a lot more easily. So a lot of these hardware implants, they get stuck in a system. They give software access. They grant software access. They escalate privilege. And then the rest of the thing, all the real malware, the fun stuff, the pop shells and stuff, that happens in software. So the hardware is in there. It does its job. It backs off and lets the software take control. It makes a lot of sense to do it this way, right? Because I mean, software developers, they're a dime a dozen, right? No, hardware guys, we're in high demand. Anyway. At least I pretend to think that. I just play a hardware guy on stage. So we have 5 implants we're going to talk about today. Blindly escalating privilege using JTAG, patching kernels via DMA on an embedded device, enabling wireless control of an off-the-shelf PLC, hot plugging a malicious PLC expansion, and a bad USB-style display adapter. So I don't know if any of you look at these lists, but there's been some rants about junk hacking, and junk hacking must stop. Anybody can go and buy a $10 device at a consumer electronics store, open it up, and do bad things to it, right? So what's the deal? Why are we talking about this at Black Hat and DEF CON and all these like world-class conferences? Well, the reason is the skills and tools and everything that we use on junk hacking is the exact same skills and tools and everything we use on critical infrastructure. You open up a home wireless router, and you open up a PLC controlling a centrifuge, and you're going to find similar chips and the same kind of board layout. So there's probably a lot of people who go and do interesting things to critical infrastructure, and they're probably under NDA, but they're probably not under NDA over like webcams and TV tuners and wireless routers. So when you see someone talking about this stuff, it's like, this is how I can present you these skills. This is how I can show you the state of the art without causing it to be too bad. Anyway, let's go on. So first, actually, I'll drink to that. Cheers. It's all vodka, water. So a blindly escape privilege using JTAG. Who's used JTAG before? Okay, anybody know what it stands for? Joint Test Access Group. That really helps you understand what it is, right? So if you kind of put it into this OSI model, you've got a physical layer where you have a bunch of pins, ones and zeros that twiddle. On top of that, you have a state machine. And on top of that, you have an interface to give you instruction registers and data registers. And we can keep abstracting all this. We get up to the next level. We have processor or target-specific information. MIPS does it different from ARM, does it different from x86. But really, we have software that abstracts all that. At the very top level, we have boundary scan. We can control the IOs of the device. We have halt resume control. And we have memory access. So we can execute what we want, and we can execute it when we want it, and we're in charge of the CPU. So if you're curious for more of this, there's a presentation from 44Con last year and B-Sides Portland last year, JTAG to root 5 ways. There's 5 different ways we went through and used JTAG to get a root shell. It's a pretty neat thing to walk through because I looked around and I realized like there's a lot of people who are hardware people who say, oh, we've got JTAG, we win. And then there's these software people who are like, well, I only speak root shell, like that doesn't help me. Like I understand I win, but how do I actually play the winning move? So came up with a couple examples of how to do this, how to take that last step. One of the interesting ones is patching Getty. Getty is a binary process. It runs in memory, and what it does is it sits there and it waits for you to connect. And when you connect, right, it passes your username on to login, and login normally asks you for your password. In order to prevent like command injection, so if your username is like -f space something, what it does is it has this dash dash at the end of the command line operations. So that dash dash says, do not accept any more flags after this. If we can go into memory and we can patch this 1 byte in memory from a dash dash to a dash f, we're passing a -F to login, and login will force authentication. It won't ask us for a password. So how are we going to do this? So this is SolderPeek. I presented this last year at Black Hat. It's a toy from the NSA playset. It's basically an Arduino board, and it has a bunch of pins that are JTAG pins. It's got an I2C flash chip that stores an SVF file, a serial vector format file, which plays back a series of JTAG commands. So we'll go and use that device. We'll pop it into a system. This is a look at what the board is. It's very simple. It's only a handful of components. It's much larger than it needs to be. You could totally customize this to fit the JTAG pinout of whatever your target system might be. In order to generate that SVF, you could go and manually go through, look at the JTAG instructions, and figure them out. Or you could just patch OpenOCD, take the debug output of OpenOCD, which tells you all the IRs and DRs it sends, and write a script and convert that into, an SVF file. The SVF file then you can play back without having to run OpenOCD, so you don't need a full stack, a full software platform for that. Anybody bored yet? No one's fallen asleep yet, but this isn't the talk right after lunch. That's the worst one. That's what I normally get. So I'm going to flip over to a demo video. So pardon my command line. Let's full screen that. Oh, that's not full screen. Well, it'll have to do. So this is the Galileo. It's an x86 dev platform. I try and log into it as root. It asks me my password. That's kind of what you would expect, right? It's really slow, too. It's a 400 megahertz, 486 class processor. So log on as Galileo. It asks us for a password. We can log in, but we're just a user. That's no fun. We want a privilege escalation. Exit. Get out of here. Now let's go back and look at our Galileo. I've got this SolderPeek all set up and programmed, and it's going to plug into the JTAG port on the back of this board. Luckily, this is a development board. It's kind of a contrived target. It already has the JTAG header there. But it's running a full Linux install. We just go over, we plug our JTAG adapter in around the 3D printed stand that I made. I'm proud of myself. It's the first 3D print I actually made from scratch. Yay, hardware. So we plug it in. It gets power. Once it gets power, it starts playing back an SVF. That SVF is going to go through to actually 4 different spots in memory and patch them. Because what I found is Getty always lives in certain spots on this platform. So I just patch them all, do it the rough way. So it's running there. It's plugged in. It's patched. So we don't see no flashing lights. We don't want our implant to announce to the world. We go back to our console. We try to log in as root, and we win. Yay, root shells. OK. So, and yeah, we are actually root. We can look at the shadow file, yada, yada, yada. Thank you for clapping. I gave a very similar presentation recently with the exact same demo video, and no one clapped. But I think it was a software audience, so I had to say, I should say, look, it's a root shell. You know it's got the thingy do, so whatever. So I know you guys are a sharp crowd then. So there's the Galileo. Oh, so I didn't have little misordering of slides. So what? It's cheap, it's simple, it's readily available. I used a custom board. You could have just as easily used an Arduino Pro Micro, which is less than 2 square inches. The payload can be prototyped with standard tools. You can use OpenOCD, prototype your payload, and then program it into this device. If the header already is there, all you have to do is plug it in there. If it's not, you might have to figure out a pinout, figure out pogos, something to do like that. It's small enough you can stick it pretty much anywhere. And here's the cool thing. JTAG is JTAG is JTAG, right? I've used this exact same device on ARM, on MIPS, on x86. Granted, like we said before, we've got that stack up. The upper layers are different. The meaning of those IRs and DRs are different. But the physical layer, the hardware, which is what matters to me, is all the same. So the next one, patch kernels via DMA to an embedded device. So what is DMA? We normally see this diagram from the PCIe specification. DMA is a situation where we have a device like this PCI Express endpoint over here. Maybe it's a network adapter, and it's receiving packets. It wants to hand those off to the system. Instead of going and handing byte by byte to the CPU, it's able to go and walk straight over the root complex straight to memory. So an endpoint can go and write to memory. This is how a graphics card is going to pass graphics stuff, frame buffer, maybe textures, whatever, between main memory and graphics memory. The point is, DMA is direct memory access. We have devices that aren't the CPU. We have other people in the system who can read and write memory. So there's a brief history. There's actually a long history of DMA attacks, but I'm going to give you the brief version. On the left, which I guess is your left because the slides are flipped. Anyway, on the left is Tribble, which is a board designed by Joe Grant and some friends of his. It's a PCI board. You plug it in, and there's a little hard drive right there. This PowerPC processor goes through and periodically reads all of memory and dumps it to a disk for later fun stuff. On the right is a PCI Express to FireWire adapter. So there's a whole, basically a decade of people talking about the fact that when you have FireWire, you have a peer-to-peer connection, and one of the profiles allows DMA access. So there's a bunch of tools you can use. You can plug FireWire devices into Thunderbolt. You can plug them into an Express card slot. You can put them in a PCI Express slot. And suddenly the system is now vulnerable. As soon as it loads those FireWire drivers, you plug a cable between the two of them and you can win. Meaning get memory and get privilege escalation, and maybe even root shells. So a couple years ago, I presented this. I actually was part of the NSA Place that I called it Slot Screamer. I found this reference board for this chip, which is a USB to PCI Express bridge. If you want to find more details of that, just search for Slot Screamer. I think I put a link in there somewhere. And what I can do is I can plug this into a PCI Express slot, and then from an attack computer, I can go and sit there and craft PCI Express packets from USB, over USB. So I write Python into PCI Express. It gets thrown over the PCI Express hierarchy, and it goes and reads memory, and it brings it back to me. What's cool about this is, everybody thinks PCI Express, they think graphics card and motherboards and x86 PCs and home desktops. And maybe you think about the fact that laptops have like a mini PCIe slot. This little blue card inside fits in a mini PCIe slot. But there's a lot of ARMs and MIPS systems now that actually have PCI Express slots as well. So this is an NVIDIA Jetson board. I actually played with this at Slot Screamer. They actually use some hardware DMA protection that I didn't spend the time to get around. But there's other devices like this. This is a $10 Pogo plug. $10 you get a system that actually supports PCI Express. It doesn't really support it because, as you see, I've soldered some wires on there, very tiny wires. I soldered them to the right pins. I put the right resistors and capacitors in there so I could wire those out to an external PCI Express slot. And then I could do DMA fun stuff. But really, $10 and the device has a PCI Express slot. That's cheaper than any device you can get to put into the slot. It's cheaper than the PCB of the board you would put into the slot. Onward. I have found this guy. It's a MIPS router. And you can see I stuck the board in there and used some high-quality electrical tape to plug it in. This is a MediaTek processor, MediaTek MIPS processor. If you look at the functional block diagram, you see it's actually got 3 separate PCI Express ports. As I mentioned before, I wrote some Python that crafted PCI Express packets that I send over USB to this device. What we're going to target this time is system ACL enforcement. So normally when you go and look at a file, it checks the permissions on the file. It calls this function generic permission, finds out if you have permission, and if you do, it returns 0. If you don't, it returns negative e-access, which is negative 13, I believe. So what we want to do is we want to go find the spot in the kernel, in memory, where this is. And luckily on a simple system, the kernel always lives in the same spot. And we're going to go and find it, and we're going to patch it and change this negative 13 to a 0, so we always win. So let's flip over to the video. And pardon the blue bars. So here's that MediaTek platform, just kind of walking through. That's the CPU. They've got 2 separate PHYs for lots of radio stuff. This one's kind of cool. It's got a flash chip that holds the whole firmware. This chip somewhere over here. I'm going to point to it eventually. There we go. That's a SATA controller, which is connected via PCI Express. And here's my malicious board plugged into the PCI Express, mini PCI Express slot. Right now, it's connected over USB to my laptop. And I have a serial console to connect to it. So let's see. We go. Here we go. We want a cat Etsy shadow. We're just a user. We look at it, and we see that it is owned by root, and I don't have permission to it. I cat it, permission denied. Well, let's work around that. We'll go over to the other window eventually. I really need to get a stand for my phone so you don't get sick watching these videos. I wrote a little script, patch generic permission. It locates the USB device. It's going to go through and find the address in memory, patch that specific address and memory, and it's done. So that's the card. Basically, a USB cable to that card went through, generated PCI Express packets, which wrote memory. Now I go back and I can cat my cat Etsy shadow, and yay! So. You know, last time I delivered this, it was after lunch, so maybe everybody was just asleep instead of clapping. If we want to go back, we can always unpatch it. We put it back to the state it was in before, and yeah, come on. I don't know what I'm doing. Oh, yeah, got to move the mouse, select the right window. Permission denied. So, yay, we secured the system. Woo! And there you go. So this is not truly an implant yet because I'm lazy. This little board has an 8051 CPU. Whenever I get around to it, I'm going to write some code for that 8051 CPU to automate all this. But as of right now, I just use a USB cable to do it in Python because I can handle Python. 8051 requires like low-level languages and compilers, which are fun and all, but that sounds like work. Tool chains are the hardest part, which is no different than hardware either, but you know. So onward. No, I don't have a what. So what? So what? Basically, these embedded devices, they are fully featured computers now, and we keep saying that over and over again. All these IoT devices, they're susceptible to all the same things that desktop computers were and laptop computers were, even down to the hardware level now, where we're adding all of these high-speed interfaces that are very highly privileged. So next, we're going to move out of the junk hacking realm and into the spoil all of your water and destroy the power grid type world. So we're going to enable a wireless control of an off-the-shelf PLC. This is a Siemens S7-200. I borrowed this from a friend. It's a kind of an old PLC. Hey, I've had a look at PLCs before. Let me open this up. So I open it up, pop it off. Oh, OK, right there. We see a chip. It's got a product number. I can look up that thing and get the data sheet. I know right away this is a RAM chip because of the pinout. I recognize the shape and form factor. And I know this is a flash chip. I can look up the part numbers. I can figure them out. I can read them. That's all well and good. That's the software approach. Yeah, tampering with firmware, that's kind of whatever. Let's look at the hardware. We got on to the next layer, and this whole board is dedicated to input and output. So if you notice, there's a bunch of output buffers that control what gets output to the outer system. It takes the low-level voltage that comes from the CPU, the GPIO output, and turns it into a relay, or turns it into like a 24-volt output. Likewise, there's a bunch of input buffers that take high voltage or something in, or analog voltages in, and condition them so they're just right for the CPU. We look down to the next layer, and that's just capacitors and power stuff, which is really fun, but there's not a lot we can do. So back up a level to this layer. We notice that there's this. Can you make out that header in the middle? I hope so. Yeah, it looks better on your screen than mine. Probably because there's not giant lights flashing in your eyes. We look at this header, we have a bunch of pins, and if we use a multimeter, we can find out that these buffers connect to these pins, which brings them up to the next layer to the CPU. These buffers connect to these pins that bring them up to the CPU. So let's take a look at that. It's kind of a double-layered 0.1-inch header. If we could intercept any one of those signals, we could control what happens on any output downstream from the CPU. So I thought, OK, this is great. I'm going to go and I'm going to make an implant. Right? This little guy is an Arduino board that costs $2 and an NRF radio that costs $1. And about like $1 worth of wire. So like the wire cost is a significant portion of the amount of cost of this implant. I stick it in there, and I want to snip one of those leads and put it in place. But again, this is someone else's hardware, and they didn't want me to tamper with it. And besides, when you do put it back together, right, you can't see it, right? The device is in there. You've taken the top off the device. You still can't see the implant. Onward, put it back together. There's no tamper evident anything. You can pop the tabs off the side, open it, close it many times. You'll never notice it. But I couldn't get software for this device. So we made no software changes, right? All the original hardware is in there. The modification that I might have made is not apparent, and one signal can be wirelessly set unset. That connector that we looked at also connects to this DB9 programming port, which would be great if we wanted to intercept the programming that was going on the device as well. So I wanted to get this working. I wanted to demonstrate it. And I went and I looked, and it was nearly impossible to get the software to configure this guy. I've later found out there's actually an open source software package that does it as well. I haven't put with that yet. So it was actually cheaper for me to go and buy a newer system and do the same thing. And I thought, OK, it's a newer system. They're gonna like have updated somewhere. It's going to be all integrated into a single chip, like progress and stuff. Nope. similar to how it was before. Actually, this goes straight down to the I/O board. The I/O board is a little different. It has one giant header instead of two small headers. You can see those white things at the bottom are the relays, and the power board at the very bottom. There was a CPU board just above, which I failed to show you. What I did notice is this thing has LEDs on the front that show you which inputs and outputs are on and off. So what I did is I looked at those LEDs, and you see there's like little gold holes underneath. So on the left are the LEDs, these white things. Right underneath them is this little hole that is a via to the other side. Those vias connect over here, down here. So I trace these signals out. They go through this buffer chip up to these legs over here. That's the bottom of the connector that goes to the next board. When I go to the next board, I look at the connector and I trace it. Right? These 4 signals right here are outputs, and they all go through this little package right here. This is a bank resistor. So it's a whole bunch of resistors in one chip because it's easier to place one chip than it is to place 4 small resistors. This resistor actually protects the input and outputs of the CPU and the other circuit. So all I need to do is solder one wire onto this one spot right here, and I can control the output of the relay without the operating system, without the software having any means of actually knowing what's going on. It's going to spit out a 1 on this wire. On the other side of this resistor, it's going to be a 0 if I say so. So let's walk at the video of installing and using this implant. Other screen. 3. So here's the little implant. Put it in a Ziploc bag because then it's not going to short things out. I soldered one leg to a ground on a capacitor, another to a power pin on a chip that I recognized and was able to get the data sheet. And that one data pin is the one that actually does the flipping of the bits. I have to get all those little itty-bitty wires so they don't interfere with things. I put it in. I'll get the top board and mount it right on top once I get things out of the way. There we go. Top board plugs on. And that's where that big chip in the middle is the CPU. It's got flash and RAM as well. Tuck those wires in so it doesn't get found. Put the case back on top. Snap. And then we are going to go turn it on, and I'm going to walk through. And I don't believe you have audio, but let's see. Does this mic work? Maybe. I'll just, what? Is it playing? Oh, okay. So it's going to beep as soon as I go start playing with the switches. This is the demo mode. I'm going to clear it and turn it on and set it. And then there's like a reset latch. I let go. I need to put the second input, and that resets it. Simple demo. That's just how they work. Put them both on, and they go on until one goes off. There you go. I'm going to go over here, and I have another wireless adapter hooked up to my laptop. Exact same hardware, just with a longer wire. And I have a little shell script. I'm basically going to send a serial command and output to 1, output to 0, and disable. So disable is high impedance. It lets the system regain control of the output. So let's look over here. When it beeps, that's the multimeter telling us that this output is on and shorted out. I'm remotely turning it on and off, and you'll notice there's no light lit up on the LED to tell us that the output is on. Right? We go, I've turned it off. It thinks it's on, but no beep, so it's off. Right? I use my software control, or radio control. I can turn it on, off, and disable it. Another fun trick I can do is I can go over, and this device has all sorts of stuff built in to make sure it doesn't do things it shouldn't do. I can go through and send a bunch of commands and turn it on and off really fast, which for some things might be really bad. Think about anything electronic that shouldn't be turned on and off fast. Onward, let's see. Half hour. So what? It's a cheap implant. It's mostly off-the-shelf, open-source code. Literally, I took the demo file and changed 3 lines to make this work. And this can be retrofitted to pretty much any I/O type. If you know where to put this wire, where to toggle that bit, you can use this on any kind of system. So onward, let's do a hot plug, a malicious PLC expansion module. This is another PLC I got. I bought it because it's the cheapest one you can buy on DigiKey. It's made by Phoenix Contact, which is actually a pretty good company. And it's a nicely well-designed thing with some decent software. But the first thing I do when I open this up is I look at it, and there's one thing that just jumps out at me and says, Joe, look at me, look at me, look at me. And it's over here in the bottom left corner. Anybody know what that is? JTAG, yay. And once we have JTAG, we have fun and win. And we can look at the chip. It's an XP LPC 1765, which I can go and get a data sheet for and know exactly how to use. Luckily, I look at the data sheet and, oh, there's code security protection. There's security. We're going to be foiled. You can disable JTAG on this chip. You can disable flash updates. You can disable it to disable access to any JTAG commands. But this is the real world. Anybody gonna guess what it was set to? Yeah, wide open. So looking at it, like this is a spot where a little expansion module plugs in, and you may not be able to see it, but in the middle is a little black header. I can't believe it. It's either 8 or 10 pins in the middle. That's where it connects. Right next to it are these pins. Like, that's nice and close. So this is the USB connector that normally goes in there that lets you program it. This is the blank that's in there when it's not in use. And that's the connector it normally connects with. That's the USB one. So if I have JTAG, what can I do? I look at the memory map of this chip, and I see that there's a range dedicated to GPIO. And there's a bunch of bits that I can use to set and unset the GPIO values, specifically the port pin value. And it tells me the address in memory that I go to, to set or unset that. I look at the relays up top. I know that that's what makes things happen. I use my multimeter and trace it down to figure out which GPIO pin of that NXP chip is the one I want to talk to. I look at the data sheet and find out what address it's at. And I'm going to make a JTAG script that's going to go in right to that address and turn on or off that GPIO. So back to a video rifle for the sharp ones will notice I only have 4 videos, yet I said 5 implants. So you're like, oh, he's going to cheat us. I'm going to cheat you. Anyway, hooking up the same way as before, we've got our little display we can go through and we can enable and disable an output using the front, and it outputs, it beeps, makes a loud annoying noise. We can reset the output or clear the override. I've got my implant that I'll pick up and show you. It's got a bunch of pogo pins, right? Those pogo pins are lined up to match with those JTAG pins. So all I need to do is plug it in, and it'll play my script because it's going to get power and go. It's set up to go, and actually here, this is what a pogo pin is if you're not familiar. It's a little like cones that tube pins that have a spring inside, so they're springy. So I pop this in. It's going to wait 5 seconds. It's going to write to that I/O port, and beep. Thank you. And the thing is, like, we just halted the processor, wrote a bit, and then stopped. And we can go, the software doesn't know that happened. It doesn't check the value of that register. All we do is hit the buttons, and we can go and disable it. There's no persistent control there. We didn't, oh, there we go again. We didn't go and change the code in memory. We didn't modify the memory. We just went straight to the GPIO. If you wanted to, you could tamper with memory. You could, write your malware, whatever the fun things you like to do with software are. You have the power to do at that point. There we go. So what? JTAG could be disabled, but it's usually not. Sometimes you get situations where it actually is disabled, but the way it's disabled is a way that you can work around with more intensive hardware hacking. At some point in time, you just have to figure out how much money you want to spend. Do you want to spend $100,000 or $10,000 and use a fib to enable JTAG? Might be worth it. Might be worth it for you. Again, that would be more invasive. It wouldn't just be an implant. Tangent. Test editors are quick and easy to access. This can be used on a unit in operation. And you can just be like walking by on a factory tour and just be like, and have it timed to, I mean, you could combine this with the other one and make it remotely controllable. You could do whatever you want. When it's hardware, all the doors are open for you, right? And when you get JTAG working, you win, right? When you have JTAG, you own the CPU, you own memory, you're in charge. Again, there's all these caveats. There's when JTAG is disabled. There's when you have hardware protections. But that's kind of what you get. So the last one we've got is a bad USB-style display adapters. And this is one that I have high hopes for, and I'm just going to show you where I am with it because it's not actually, I haven't turned it into an implant yet because I'm busy and lazy. So there's been some previous presentations actually from the NSA playset. There's this one on the left is Blinkerkopf. It was basically a modified VGA cable that you'd let's say, install a bunch of these, and they would use infrared communications to make like a little mesh network and exfiltrate data over I2C. Fun stuff. You think about a Faraday cage, right? It's supposed to keep everything in and out, but it's just a mesh of copper. Like lights that flash around might actually not get through unless you're in a fancy place that has infrared communication blockers. On the right, we have Alloy Viper, this cable over here. It looks like a Thunderbolt to VGA adapter with a sketchy old VGA cable, but this is actually a Thunderbolt cable that goes all the way through and connects to this box which contains a slot screamer, and it daisy chains an actual VGA adapter so that you can go and plug in. So like I could have plugged in right here to a sketchy VGA cable with it. Oh, they already have the adapter for my MacBook. Everything shows up on the screen just as normal, but in the meantime, there's a box under the table that's copying the contents of my memory. Well, so USB-C is this new thing. It's like this magic thing the new MacBook has. So they have this pretty, like, the ability to connect everything you need. The idea with USB-C is they wanted to make this the universal port, like universal serial bus. So they combined a whole bunch of different protocols into it. Just like where Thunderbolt was this interconnect that you just DisplayPort or PCI Express, USB-C allows you to do DisplayPort if it's Thunderbolt enabled. It allows you to do PCI Express. It allows you to do all this stuff over a single port. What's interesting is what's in these adapters. So if you have the new MacBook or I think the Chromebook Pixel, the only port you have is a USB-C port. It's even used for charging. So you have to pay $80 for this fancy cable that gives you power, display, and USB to do anything, right? So you plug that in, and you plug a hub in, and you plug your remote in, and then you plug everything else in. That's why it costs $80. There's also probably like $70 worth of shielding wrapped around that I already peeled off. The $20 version is like the cheap one you can get on Amazon, which is the one I normally use, but instead I'm using this one, which is also ripped open. This is neat. It's firmware updatable. We'll show you that in just a second. If we look at the Apple ones, though, what do we see? JTAG. So again, I've noticed this. I've hooked it up. It is, in fact, JTAG. I haven't poked at it or modified or flashed anything. But think about it. We've got this device. It's the trusted device we carry around with us. It's the one we plug in when we present. And this is not a passive device anymore. We're not dealing with a display adapter. We're just dealing with an expansion to our system that is potentially got very low-level access to the hardware. That also does display. So let's look at the cheap one. Right, we rip it open. You've got one chip right there. Again, USB-C can do native DisplayPort. Inside here, there's a little chip, and that does the DisplayPort to VGA adapter protocol changing. And then the next thing we look at, this chip is an NXP chip that is a USB power delivery chip. And this is what negotiates with the host to say, hey, I'm a VGA adapter, which means I need 5 volts at 500 milliamps. Please send me that power. Which seems reasonable, right? Except it might also say, hey, I'm a laptop, send me 20 volts at 4 amps. And that can make bad things happen to devices that weren't expecting 20 volts to suddenly be rushing down the USB wires. But what's really interesting on this one is this chip. And this is another NXP chip. It's a USB device. This is what tells the system that it's a display adapter. We plug it in. It says, oh, you're a display adapter. Let me turn on display stuff and ignore the rest. What I noticed, though, you ever heard of DFU, Direct Firmware Update? This chip is firmware updatable over USB. Yay! We just plugged it in over USB. So I can dump the firmware off of that, go through, tamper it, modify it, send it back. And my objective of what I'm going to do with this one, not the one I use when I present, but the one I'm going to share with other people who I know that present and I want to play a nasty trick on, is I'm going to have it set up to do the forward and back buttons, right, as a USB device. So you plug this in, you think it's your display adapter. It also shows up as a unit interface device and lets you advance slides, and it's just going to randomly advance their slides for them. I think that's a fun prank. I don't have a video demo. I haven't done that yet. It's just my plan. So pardon I guess I always worry that I'm going to over-promise and under-deliver in a talk. I hope I haven't done that because I said 5 and I'm only giving you 4.5. So please forgive me. That means, on the ratings, you just give me a 4.5 instead of a 5, right? So DFU util, it's free software. You go and you open and you can dump the contents of that firmware and you can modify them and write them back. It's an ARM M0 core, so as long as you know how to write ARM code, you can do fun stuff with that. So what? When we have only one port, that port can do anything. It's an implant designer's dream. Hardware isn't just hardware anymore. There aren't passive devices, right? I mean, even in the class that I teach, we play with HDMI. Everybody knows that somehow the cable tells the system what the resolution of the display is. In order to do that, it has to communicate. It's a two-way communication over HDMI. All these things that we think are passive devices are not anymore. The other sad thing is there's no reasonable way for a user to know what a device does, right? If I go to the Apple Store and I tell them I want to display something and they give me this, like, okay, it's a plastic box. I got it from Apple. It's sealed, except for this one isn't sealed. We need to have a better way of actually telling people what is inside and what is actually working. So today's implants, We did blindly escalating privilege using JTAG, right? We patched kernels via DMA on an embedded device. We enabled wireless control off the off-shelf PLC. We hot-plugged this expansion device, which actually used the same JTAG code and hardware as the first example, but on a very different setting. And then we talked about how we could just take a device that everyone trusts and someone you could buy off a store online and plug it in, and it's just not going to do what you think it does, even though you think it's such a simple adapter. So look at this. This is all but the DisplayPort stuff stacked up on a $20 bill. And so this solder peak, couple bucks. You could do it with an Arduino board and some pogo pins like I did here, less than $5. The Arduino plus the NRF, $3 worth of hardware, some wires. And over here we've got the slot screen, which is kind of pricey. It's like $60 to $70. But if you're dead set on making an implant, I think that's well within your price range. The point is, between $5 and $75, a hobbyist could build these. Many of them are actually published on the NSA Playset website and GitHub if you're interested in building your own. They weigh less than an ounce. They can be customized. They're all pretty universal. Once you get down to the lowest level of the hardware, ones and zeros are voltages. And it doesn't matter whether you're MIPS, ARM, or x86. It's all the same. It doesn't matter if you're an embedded system. It's all the same. So you can customize these pretty easily to many different targets. And this, I really think, barely scratches the surface of what's possible. These are a bunch of things I built in my spare time. I don't actually sell these. I don't have any government contracts where I supply hardware implants to anyone. That would be pretty cool. Actually, it wouldn't be pretty cool. I would kind of not be interested in doing that if you're thinking of asking me. But this is what I do for fun. So if you're funded, if you're a state actor, this is well within what you should be aware of and you should be able to do with very little time and effort and money. Hardware is cheap. Standard interfaces really are standard. Automating these little devices is trivial. If you can't trust the hardware, you can't trust the software, right? If you can control the hardware, then in some way, shape, or form, you can control the software, okay? Those are my takeaways, and I'm going to leave you with another philosophical thought. So there's a story about the 3 vinegar tasters, and there's lots of old images, pictures of these guys. So on the left, we've got actually, I don't know which is which. I think the left is Confucius, right? He tastes this jar of vinegar, and it says, oh, it tastes sour, because vinegar is wine that has been polluted, that's past its prime, it's spoiled. Clearly, this represents the conference goer who missed the open bar. Right? Now, the next one is Buddha, right? He tastes the vinegar and he says, oh, this tastes bitter. But life is pain and suffering. That's what we should expect, and we should just deal with it. He's probably an incident responder. Okay. Lastly, we have Lao Tse, and he's smiling. He tastes the vinegar, and he's like, oh, vinegar, I know what I'm doing. And he goes and gets some peroxide and some salt, and he mixes it up, and he uses that to etch his PCBs to make his hardware implants. So